Hello everyone, welcome back to Act of Learning. This will be our final video in our short series on rectification of curves. In the first two videos, we saw how mathematicians were able to find the arc length of the famous logarithmic spiral and the equally amazing cycloid curve even before the invention of calculus. In case you haven't seen them, please do watch those videos. I'll leave the links to the videos in the description below and I'm sure you will definitely enjoy them. Even after these rectifications, the notion that mathematical curves cannot have lengths like that of straight lines was still strong among many mathematicians. Notably, Descartes held the view that curves like the logarithmic spiral and the cycloid were mechanical rather than algebraic or mathematical curves, and hence finding their arc lengths cannot be considered as true rectifications. He was partly right. If you watch our videos that explore the rectification of these curves, we did not use or even need the equations defining these curves. We just made use of the mechanical definition of the curves to find the respective arc length. However, Descartes was proven wrong by a relatively unknown English mathematician named William Neal. William Neal, who was just 20 years old at the time, proved that we can indeed calculate the arc length of a purely algebraic curve by finding the arc length of the semicubical parabola. The semicubical parabola is a curve defined by the equation y equal to some constant times x power 3 by 2. Unlike the cycloid or the logarithmic spiral, we are not defining this curve with a combination of mechanical motions. It's a mathematical curve. In this video, we will see a modified version of Neal's proof along with the contributions from other mathematicians that enabled him to achieve this impossible result. Neal's proof starts with one of the most familiar curves known to us, the parabola. Not this one, the other one defined by the equation y square equal to x. For the purposes of our problem, we only need the upper half of this parabola. Archimedes showed us that the area of this parabolic segment is 2/3 of its bounding rectangle. Thus, we see that the area of this parabolic segment of width x is 2 by 3 times the base of the rectangle x and the height of the rectangle square root of x, giving 2 by 3 times x power 3 by 2. The semicubical parabola thus becomes the area curve of the standard parabola. The y-coordinate at each point measures the area of the parabolic segment up to the corresponding x-coordinate. For the sake of clarity in the argument that follows, let's flip the parabolic segment with respect to the x-axis. Before we go any further, Neal's proof requires that we have a way to construct tangents to the semicubical parabola at any given point. Remember, this proof was completed before the ideas of calculus was discovered. We cannot talk about tangents in the proof without showing how to construct them in the first place. Fortunately, the problem of constructing tangents to curves was much more famous at that time, and both Fermat and Pascal, among other mathematicians, came up with their own methods. But the idea that we will be using in our video belongs to an eminent English mathematician, Isaac Barrow, who was Newton's tutor and scientific advisor at some point of time. Though vastly simpler, his idea applied only to a special class of curves, and the semicubical parabola happens to be one of them. According to Barrow, to construct a tangent at point P on the semicubical parabola, first draw a vertical line through P. Let this line intersect the x-axis at O and the parabola at P'. Draw a unit circle with O as center and label the point along the x-axis as Q. Barrow proved that the line through P parallel to the line joining Q and P' is the required tangent to the semicubical parabola. We'll see the details of Barrow's proof and how it can be used to construct tangents to a wide class of curves in a later video. For now, let's proceed with Neal's proof of finding the arc length. The idea now is to construct a line tangent to the unit circle parallel to the curve's tangent line. The point of intersection between this line and the vertical green line defines a new point T. As point P moves along the curve, T traces a curve defined as the auxiliary curve of the semicubical parabola. To see why we went through all this trouble to create this auxiliary curve, consider a tall rectangle symmetrical above the vertical line, with one of its sides passing through T and the opposite side along the x-axis. Extending the sides of the rectangle, we can construct a right triangle with base the same as that of our rectangle, such that the hypotenuse of the right triangle lies along the tangent of the semicubical parabola. Note that even at this scale, the hypotenuse of the triangle approximates the curve quite well. We are now going to make a series of observations, all based on nothing more than the similarity of right triangles. It is obvious that triangle TOT' is similar to triangle TSO because they have angle T in common and both are right angled. Therefore, TO by OT' equals TS by SO. Because line TS is parallel to PR, triangles TOS is similar to triangle POR, and therefore TS by SO equals PR by RO. Again, because of the similarity of the right triangles PRO and LMN, we see that PR by RO equals LM by MN. This shows that OT' times LM equals TO times MN. OT' is just 1 because it's a radius of a unit circle. TO times LM is the area of the rectangle we started with, and LM is the length of the hypotenuse. So this equation here tells us that the hypotenuse of the right triangle is numerically equal to the area of the rectangle. We can repeat the same process at different points on the semicubical parabola, with each triangular area equaling the length of the corresponding tangent segment. As the width of the rectangle gets smaller and smaller, we see that the total area of the rectangles approximates the area under the auxiliary curve, and the sum of the tangential segments approximates the arc length of the semicubical parabola. So if we know the area under the auxiliary curve, we would have successfully found the arc length of the semicubical parabola, and that solves the problem. Finding the equation of the auxiliary curve is straightforward. It is very clear that triangles TOT' and P'QO are similar. Therefore, TO by OT' equals P'Q by QO. Because OT represents the y coordinate of the auxiliary curve, this shows that the equation of the auxiliary curve is square root of 1 plus x. This is just another parabola shifted by 1 unit to the left along the x-axis. So the area under the auxiliary curve, which is numerically equal to the arc length of the semicubical parabola, is just the total area of the auxiliary curve minus the area that lies to the left of the y-axis. This simplifies to 2 by 3 times 1 plus x power 3 by 2 minus 2 by 3. Like the previous 2 videos in this series, here again we showed how Neil was able to solve a rectification problem without using calculus. But it is clear from his approach that the ideas of calculus were already known to the mathematicians of his time, which years later Newton and Leibniz formalized and used to great effect. With this video, we conclude our short series on the rectification. Hope you liked them all. Thanks for joining me, and see you in the next video.